Hello, Algebra 1. This is section 9.6 and 9.7. We've got a couple different kinds of word problems that we're going to look at. We're going to just do a couple examples of each one for you. Remember, there's also lots of good word problems worked out for you in your textbooks, so be sure to refer to those examples as well. In section 9.6, we're looking at wind and water current problems. So when you're traveling through air, the air current can affect your speed. So if you're traveling with the wind, it can increase your speed. If you're traveling against the wind, it can decrease your speed. And then when you're traveling by boat in the water, particularly if you're going like on a river, if you're going upstream or downstream, the current also affects your speed. So when you're going with the current, it helps you go faster. When you're going against the current, it slows you down. So your rate when you're traveling, either through the air or on the water, if you go with the wind or the current, then you're going to add your rate plus the rate of the wind or the current. So this is when you're traveling with. Okay. The other thing, if you were going to travel against, then you would take your rate minus the wind or the current speed, and that's when you're traveling against. All right, and then you can also just be traveling in still water. When you're traveling in still water, then your rate is just your rate. So if you're going with or against a current, that will affect your rate. So let's look at some problems that talk about wind and water currents. So I'm going to read some problems from you that are not in your book, just so you'll have some examples, some additional examples to refer to. So for this first one, I'll read it one time for you and then we'll talk about it. A plane can fly 3,750 kilometers in 3 hours with the wind. The plane takes 5 hours to travel the same distance flying against that wind. Find the rate of the plane in still air and the speed of the wind. All right, so you know when we're solving word problems, we always need to start by defining our variables. So let's start with, we're going to let R equal the rate of the plane in still air. So R is the rate of plane in still air, and this is measured in kilometers per hour. And then we'll let W equal the rate of the wind. And that's also measured in kilometers per hour. So we've got two things happening. We've got the plane is traveling at a certain rate, and then the wind is blowing at a certain rate. So for one part of the for one part of the trip, the plane is flying with the wind. The wind is helping blow it faster. But then it has to come back that same distance going against the wind. So it's pushing against the wind. It's going to be slowing it down. So let's look at what we know. And it can be helpful to make a kind of a little table for this. So if we're traveling with the wind, or we could be traveling against the wind. Now, we're talking about travel. Hopefully you remember that rate times time equals your distance. So we're going to keep with that formula. It's been a little while since we've seen it, but we've looked at it before. All right. So with the wind, you've got the rate of the plane is R. The time is 3 hours. I had to read back, sorry. A plane can fly 3,750 kilometers in 3 hours with the wind. So the rate with the wind is 3 hours. And it goes 3,750 kilometers. Okay? Then it's going to go against the wind. So the rate against the wind, we have to subtract. That takes 5 hours. And we're still going 3,750 kilometers. We're taking the same trip. We're just going in the opposite direction, but we're traveling the same distance. So again, these numbers are coming from the problem. A plane can fly 3,750 kilometers in 3 hours with the wind. The plane takes 5 hours to travel the same distance against the wind. All right, so if we multiply across, we know that rate times time, 3 times W plus R should equal 3,750. So that's this first row. So if we distribute 3R plus 3W, actually I'm going to do that differently. I'm sorry, guys. You can distribute it. It's not going to help us at this point. We're going to do something else. We're going to divide both sides by 3. So if we divide by 3, it's going to cancel out. R plus W equals 1,250. So this is from the first row with the wind. Okay. I'm going to do the same thing against the wind. So for against the wind, it's 5 times R minus W still equals 3,750. So again, rate times time equals distance. Rate times time equals distance. That's what this is. I'm going to divide both sides by 5. That's going to cancel out. R minus W and equals 750. And this is against the wind. Okay, so we have two equations. We've got R plus W equals 1,250. R minus W equals 750. If you have two equations, you have a system of equations. So I'm going to put those together. We've got R plus W equals 1,250. And then R minus W equals 750. Okay, some methods that we've talked about in this chapter. We've talked about using the substitution method, or we've talked about how you can add or subtract two equations together and get one of the variables to cancel out. I call that the elimination method. This one is set up really nicely for that method because if we add these two equations together, the W's are going to cancel each other out. So I'm going to go ahead and do that. I'm going to add these two equations together. So R plus R gives me 2R. W minus W cancels out. And then 1,250 plus 750 gives me 2,000. All right, I'm solving for R, so I'm going to divide both sides by 2. And R equals 1,000. Okay, now we can find W. R plus W equals 1,250. So 1,000 plus W equals 1,250. If we subtract 1,000 from both sides, we know that W equals 250. So we've solved for both variables. We remember that R is the rate of the plane. So the rate of the plane in still air is 1,000 kilometers per hour. And we remember that W is the rate of the wind. So the speed of the wind is 250 kilometers per hour. So we used a system of equation and we solved for the rate of the wind over here and the rate of how fast the plane was traveling. All right, let's try another one. Let's do a problem with a current, since that's the other thing that comes up in this section. Okay. All right, again, I'm going to use a problem that's in the, that you don't have access to. So I'll read it to you. This will just give you some extra examples besides what's in your book. So for this one, Jim can row a boat 30 kilometers downstream in 3 hours. I'm going to make some notes this time. 30 kilometers downstream in 3 hours. But it takes him 5 hours to return. So if he's returning, then he's going upstream in 5 hours, and he's returning to where he started, so he's still going 30 kilometers. So 30 kilometers downstream in 3 hours, 30 kilometers upstream in 5 hours. What is Jim's rate in still water, and what is the rate of the current? So we're trying to figure out Jim's rate in still water and the rate of the current. Okay, so again, it can be really helpful to start with a table to help you organize what you're doing. So we've got going downstream and going upstream. And we're still using our formula, rate times time equals distance. Okay, so for this one, if he's going downstream, picture the stream, the water's flowing, he's letting the water push him along as he goes downstream. So when you're going with the current, it's your rate plus the rate of the current. Oops, I forgot to define my variables. All right, so let's let R equal Jim's rate and C equal the rate of the current. Okay, so if Jim is going downstream, he's going with the current, so R plus C. That trip takes him 3 hours, and he's going 30 kilometers. When he wants to come back, he's going against the current, so R minus C. That takes him 5 hours, and he's traveling the same distance, 30, because he's going back to where he started. All right, so if we work our way across here, we have the rate times time is going to be 3 times R plus C equals 30. Divide by 3, R plus C equals 10. So there's our first equation. If we take this bottom row, 5 times R minus C equals 30. Divide by 5, R minus C equals 6. So there are my two equations. I've got R plus C equals 10, R minus C equals 6. That gives me my system of equations. And these are very nice and simple. There's not even really any big coefficients to worry about. I can add or subtract the equations together. So it looks like if I add these together, these C's are already going to cancel each other out. So I'm going to do that. I'm going to add the equations together. R plus R gives me 2R. C minus C cancels out. 10 plus 6 gives me 16. Divide both sides by 2, and R equals 8. Now I just need to figure out C. R minus C equals 6. You can use either of these original equations. 8 minus C equals 6. Well, 8 minus what equals 6? Has to be 2. Okay, so in still water, R stands for Jim's rate. So Jim can go 8 kilometers per hour in still water. C is the rate of the current, so the current is going 2 kilometers per hour. All right, so that's one wind problem and one current problem. Now I'm going to flip over to section 9.7. This is just another set of word problems they don't have to do with the wind or the current, but they're word problems, so they all kind of go together. These are called puzzle problems, and they also can be solved using tables. So let's look at a couple of these. Now I'm on 9.7. Puzzle problems. These are the kind of problems you think about when somebody's trying to just like make up a math problem off the top of their head. This is kind of what they sound like. So I'm going to read the first one to you. The sum of the digits in a 2-digit number is 15. So sum of the digits and a 2-digit number is 15. If the digits are reversed, the new number obtained is 9 more than the original. So if reversed, new number is 9 more than the original. Find the original number. So let me read through that one more time. The sum of the digits in a 2-digit number is 15. If the digits are reversed, the new number obtained is 9 more than the original. Find the original number. So that definitely sounds like a puzzle. It fits its name. So let's look at how we would do that. We're going to start by defining our variable. So we're comparing the digits to each other. So let's let t equal the tens digit of the original number. And I'm going to let u equal the units digit of the original. All right, units is like the ones, but we don't want to use O for ones because then it might look like a 0 and we might get mixed up. So T for the tens digit, U for the ones or the units. And then we've got an old number and a new number. Then we've got the tens place, the units place. Again, that's the ones place. And then we've got the value of the number once we put it together. So in the original number, the old number, the tens digit is T and the ones digit is U. We know that the tens digits are worth 10 each. So like if we had the number 53, this would be 5 times 10 to make 50, and then plus 3 to make 53. So we've got 10 times T plus U. Then it says we reverse them. So now U is going to go over here and T is going to go over here. That means that now this is in the tens position. So now this one is worth 10 and this one is worth 1. So we have 10U plus 2. So my original number is 10T plus U. My new number is 10U plus T. So let's talk about what we know. The sum of the digits in the 2-digit number is 15. So the tens digit plus the ones digit is 15. Okay? Then it says, if the digits are reversed, the new number obtained is 9 more than the original. So let me write that over here. New number is 9 more than the original number. See how that kind of makes an equation? The new number is 9 more than the original number. Well, what's the new number? The new number is 10U plus T. That equals 9 more than the original number. What's the original number? 10T plus U. So there's my next equation. I've got 10U plus T, looks like I wrote the word out, equals 9 plus 10T plus U. All right. This is my second equation. Let's see if we can clean it up a little bit. So we've got 10U plus T equals 9 plus 10T plus U. Let's move the U over here. So subtract U. That gives me 9U plus T equals 9 plus 10T. Let's bring the 10T over here. So we're going to subtract 10T. 9U, and then 1T minus 10T is negative 9T equals 9. So now we've got an equation that we can use, but notice how everything here is divisible by 9. Sorry, I had a hiccup. We're going to divide everything by 9 just to make it easier for us. Divide all the parts by 9. As long as we do it to everything in the equation, we're allowed to do that. So that gives me u minus t equals 1. Okay, so I'm going to put that up here. U minus t equals 1. So now I've got these two equations. T plus u equals 15. U minus t equals 1. Ooh, those look really similar to each other. Let me just change this. I'm going to rearrange it and make it negative t plus u equals 1. So that way the like parts will line up. Negative t plus u equals 1. I just switched the t and the u so that it would match up with what I had over here. All right, so these are all set. If I add these together, t minus t is going to cancel. U plus u gives me 2u. 15 plus 1 gives me 16. Divide by 2, and u equals 8. So I have the ones digit from the original number. Okay? I'm going to take that number, put it back in either of these two equations that I started with. I'm going to pick the top one. So t plus u equals 15. Put 8 in place of the u. T plus 8 equals 15. Subtract 8 from both sides. And t equals 7. Okay? Now this one's a little bit different than normal because we don't want to say u equals 8 and t equals 7. The question is, what is the original number? Well, remember, the original number, the t stands for the tens position, and the u stands for the ones position. So if I make these into a number, the tens position is 70, and the 8 position is 8. I'm sorry, the ones position is 8. So I have 78. T is the tens place, 8 is the ones place. 78. If you reverse that and you make it 87, it is 9 more than 78, which is what the problem said. All right, one more to go. One more puzzle problem, and we'll be all set for the day. All right. 9 years ago, Frank was half as old as Marilyn. Now his age is 2/3 her age. Find their ages now. Okay, so we have Frank and we have Marilyn. I'm going to say that Frank's age now is going to equal F, and Marilyn's age now is going to equal M. So let's read the problem again. 9 years ago, Frank was half as old as Marilyn. Now his age is 2/3 her age. Find their ages now. All right, so we've got Frank, and we've got Marilyn. We're going to make a table. Let's see. We have their ages now, and then it talks about their ages 9 years ago. So this is just going to kind of help us think through this. Their ages now, we decided, are going to be F and M. Okay, 9 years ago, how old were you? Think about it. Take your age now and subtract 9. That's how old you were 9 years ago. So Frank, 9 years ago, would have been F minus 9. And Marilyn, 9 years ago, would have been M minus 9. All right, so let's read through the problem again. Let's see. 9 years ago, Frank was half as old as Marilyn. So 9 years ago, Frank, this is 9 years ago, Frank was half as old as Marilyn. So his age 9 years ago was half of her age 9 years ago. So that's my first equation. Frank's age 9 years ago is half of Marilyn's age 9 years ago. Now his age is 2/3 her age. So Frank now is 2/3 Marilyn now. Frank now is 2/3 Marilyn now. So this is my system. This one looks a little more intimidating because it has the fractions in it, but we can do math with fractions. We don't need to let that scare us. All right, So you might notice for this one that this is set up nicely for substitution. The f is already by itself in this equation. So that means that we're ready to substitute this value in place of the f in the other equation. And that's what I'm going to do. I'm going to substitute 2/3 m in place of this f minus 9 equals 1/2 m minus 9. All right, so we just have to be careful here. Don't let the fractions keep you off track. So we're going to distribute this 1/2. 2/3 m minus 9 equals 1/2 m minus 9/2. I just multiplied everything by 1/2. Now I have m's on both sides of the equations. 2/3 is bigger than 1/2, so I'm going to move this one over here. I'm going to subtract 1/2 m from both sides. All right, so we've got 2/3 minus 1/2. You can use a calculator or you can use a common denominator. Our common denominator would be 6. So I would have to multiply this one by 2/2 and this one by 3/3. So 4/6 minus 3/6 equals 1/6. So 1/6 m minus 9 equals negative 9/2. Okay, we're trying to get the m by itself, so let's add 9 to both sides. 1/6 m, so we have negative 9/2 plus 9/1. If you want to make a common denominator, you're going to have to go with 2. So we're going to multiply this by 2/2. So we have negative 9/2 plus 18/2. Negative 9 plus 18 gives me positive 9. So that's going to equal positive 9/2. Almost there. I want the m by itself. Right now it's being multiplied by a 1/6. I'm going to multiply both sides by the reciprocal. So I'm going to multiply both sides by 6/1. All right, so that will cancel, and I'll have m over here. I have this 2, can reduce this 6 down to a 3, and then 9 times 3 gives me 27. So m equals 27. That means Marilyn's age now is 27. So we're halfway there. We just need to figure out Frank's age. So Frank's age is 2/3 of Marilyn's age. So it's 2/3 times 27. The 3 and the 27 can reduce down to a 9. So 2 times 9 gives me 18. So Marilyn is 27 years old now, and Frank is 18 years old now. All right, so sounded like a tricky problem, but we defined our variables. We set up a table to help us kind of organize what we were talking about, because we had to compare how old they were now to how old they were 9 years ago. Then we used the information from the problem to help us write our system of equations. For this one, we decided to use the substitution method. So we substituted back into the equation. Then we just did the algebra to solve for the first variable. And then once you have the first answer, you plug it into one of your equations and solve for the second. All right, so that's everything for 9.6 and 9.7. Hopefully these extra examples will help you navigate some of these problems. Try to use a table when you can. They're very helpful for the wind and water current problems. There's lots of examples in your book also, so remember to look through those examples. Really look at them step by step. Make sure you're understanding how things are changing from one step to the next before you just go on to the next example. And when you get stuck on the homework problem, go back to the examples and see if there's an example that matches what's happening in the problem that you're working on. Maybe you can model your problem and set it up the same way as that example that you're looking at. If you have any questions, please send me an email. I'm still checking emails every morning, and I'll be happy to get back to you and answer your questions. I'm looking forward to going back to school next week, so hopefully a lot of you will get to come back. If not, we're still going to try to do some videos for you, so stay tuned, and I hope you're doing well. Remember, everybody, there's strength in numbers.